like we got everything. Welcome to the Northwest C++ Users Group. This is the February 2026 meeting. And we'd like to thank City of Bellevue for sponsoring our meeting room. We'd also like to thank CyberData Corporation for sponsoring our Teams account.
Thank you, CyberData.
I did finally update the code of conduct slide. Essentially what Bellevue City Hall has is not easily consumable as a slide. So basically, be respectful to everybody else. If you really want to see the Bellevue City Hall Code of Conduct, it's available at the service desk. You can get it as a pamphlet or it's actually on a very large wall plaque. And still looking to get the after meeting meetup going again. I don't know, Peter, we could talk about that at some point. At the moment, I don't know, we got enough people here to really make it viable.
Gordon and I will probably go to dinner even if there's nobody else here to go.
Oh, okay. Maybe we'll just do it that way for a little while for ad hoc, because it's, yeah, at least for me, which is the only other person in the room at the moment, I'm usually shot by the end of the meeting, so I don't attend those too often. We are currently booked here at the Bellevue City Hall through mid-2026. We plan to stay here as long as we can. This is actually working out quite well. For folks that are remote and possibly looking at traveling, I'm going to start promoting this this meeting, next meeting, and it really takes effect April meeting. We are right across the street from the Bellevue Transit Center, where the light rail comes in. Folks in the Seattle area, if you take the light rail, they call it line 2, and it goes across the Puget Sound or across the lake, opens up at the end of March. So if you're in the Seattle area or on the west side, it'll be very easy to get here if you just take the light rail across the lake, starting at the end of March. So for the April meeting, assuming everybody's schedule holds, that'll help. I am also starting, it's not on the slides, but I'm also starting to look at speakers for the second part of the year. I think we're in pretty good shape so far. We did a survey, and I got the results back from that. Kind of what we were expecting. I can send them around if people really want, but generally, people were interested in intermediate to advanced topics. There were some beginners, but most people wanted intermediate or more advanced topics. And I actually probably should have just brought the thing and shown it here, but I forgot to do that.
That might be good to do with the announcements at our next meeting.
Yeah. I'll remember to do that. And the next one was pretty much more concrete, less theoretical talks. So things that, people could use more immediately. And then pretty much the normal association of tools, libraries, techniques, and a little, some AI stuff. So nothing earth-shattering. I'll try to remember to bring those next month, and then we can just go through the deck. We'll do our feature presentation here in a moment. I'm the speaker. You get to listen to me talk for even longer. Sorry about that. We got plenty of time, so feel free to ask questions. This is going to be a fairly quick presentation. Okay.
That's our feature presentation like that. I feel like I should be going out and coming back with some popcorn.
Yep. Okay. And so tonight we're going to talk about saturation arithmetic. The topic for this actually came about, this was my backup presentation from last year and it's dated, so I had to use it. But it actually came about from kind of a pre-meeting discussion we were just having in the room while we were waiting for things to get going a while back. And I came across the C++26 specification. And so I thought, oh, that sounds like a good topic. We'll do that. So we'll first talk about what saturation arithmetic is, why you would use it, It is currently available in a couple of compilers, even though it's a C++26 feature. It's a small feature and fairly straightforward. We'll go over the library calls. We'll look at the implementation and efficiency. That'll probably be the meat of the presentation. There's a couple interesting implementation differences, and then a couple of alternatives. So feel free to ask questions or whatever as we go. This is a fairly short presentation. So what is saturation arithmetic? Basically, it's a mode of numerical computation where the results are clipped. So the idea is you don't wrap around or produce undefined values when an overflow would otherwise occur. You always give a given known value. If the resulting value is greater than the maximum value for the data type, you just use the maximum value of the data type. Same thing for the minimum. So you just run it to the rails, cut it off, and that's that. And there's good cases and bad cases for this. Why do you want to use it? The key is the results are guaranteed to fit into the resulting data type. So your accuracy and range are going to be compromised. I mean, you just can't go where you can't go, but it avoids undefined, wraparound, or modular results. And sometimes that's exactly what you want. The times when you want that are when you generally have natural limits to whatever you're trying to represent. A couple of examples: if you're doing video, RGB values are typically in the range of 0 to 255. So if you're going to go to 257, hey, just go to 255. It's, saturated, it's the top end, it's what you want, same thing. Audio values typically go to 16 to 24 bits. If you've done audio, you may or may not get a distortion when you saturate, but what you will not get is necessarily a chirp. So if you let it wrap around, you're going to get a noise spike in the result, where if you saturate, you're more likely to get away with it. Still may sound, you still might hear it, but it's not going to be as obtrusive. Real-world sensors also saturate at their limits. Anytime you're using an analog to digital converter, it's got both a high and low limit on it. And this also goes for actuators. So analog to digital conversion and digital to analog conversion. Oftentimes you just want to saturate. And if you do modulo, you're going to get a discontinuity or a spike. Okay, availability. Basically, the saturation arithmetic is targeting C++26. However, and these are slightly dated, so you might want to update this. GCC 14.1 supports the full set, and so does Clang 19.1.0 and Clang 16.0.0 for Apple. In the case of GCC and Clang, they are supported for both X86 and ARM architectures. From CPP reference, I've got the link down there. We'll have the slides available. And then the standards paper is down there as well. It's P0543R3. Okay, to use this, you basically have a set of compiler flags. For GCC 14.1, you set std equal to C++26. Same thing for Clang. And then I've set the 03 optimization as well. So you don't necessarily need 03, but I want to look at, as we get into this, I want to look at the assembly code, because that's kind of the interesting part of how does this really get implemented in assembly and what's the performance impact. So I turned the optimizer full on. The library calls are pretty straightforward. Add saturation, subtract saturated, multiply sat, div sat, and then saturate cast. So you've got all the 4 basic arithmetic operators. And they're kind of what you would expect. We've got some examples of that coming up shortly. Note, these are templates. They are not defined for certain character types: bool, char, wide character T, char 16T, char 32T. These types are not intended for arithmetic. So the arithmetic operator is not, these operations are not defined for those data types. Okay, so the next set of slides are basically done with Godbolt. And what I've done is just taken a very simple function and called a couple of interesting APIs, and then we're going to see how this implements in assembly language. So, and we're going to look at it for GCC, basically a 2x2 matrix. GCC versus Clang on one axis, and X86 and AARCH64 on the other axis. Yeah. Yep, okay, got that right. So this, the one we're looking at here is basically GCC for ARM. And if you look at the right, we won't get too much into the assembly, the details, but it's pretty straightforward. If you look at the assembly code, it basically moves a value. It does an add and tests for a bit flag, which is for overflow or saturation, and then branches. Okay, so pretty much what you would expect. The one thing to note, this is important because these flags, overflow or saturation, whichever one you want to call it, depending on the architecture, are not available in C or C++. So that's kind of where the library comes in. If you do this without the library, you have to do things like check if it's less than the number you tried to add to, or some various other workarounds, which are more time consuming. Essentially, this just checks the flag and it returns the saturated value, which is the .L7 label, setting up a saturated value. Yes.
So maybe you're going to get there, but it looks like this is clamping it to the maximum value that the underlying data type can hold. What if you want to clamp it to 255 for RGB pixels?
Okay, so that gets to the data type that you're passing in.
Right, but what if it's a range that's not well covered by data type, like 0 to 360 for degrees?
Then this library isn't going to help in that case.
Okay.
So yeah, so basically the the add, subtract, multiply, and divide are all tied to the data type. There is an interesting one, which is saturate cast, and that will clamp to the range of another data type. So you can do that, but there's nothing for an arbitrary, clamp to 0 to 32, say, right? Standard library has something for that. I can't remember it off the top of my head, but that's what I would go to for that. Okay, and let's see. Okay, so that's GCC ARM. GCC X64, if we look, it's a bit longer in terms of instructions, but it's basically the same thing. You do the addition, you look at the overflow bit, and then you return a value, or if the overflow bit is set, you jump down to another piece of code that puts it in the saturated value. So it's a little less efficient, but at least in terms of opcodes. I did not try to profile these and see which was actually more, more machine cycles or something like that. Different enough. This is where it gets interesting, though. So this one is Clang for ARM. And what you notice is it does the addition. It does a test, which is looking at the high bit. Let's see, EOR, yep, looking at the high bit. And then it does this C-cell operation. What C-cell does is essentially determines which value to return based on a flag, right? The key is there's no branching. This is going to perform, I wouldn't say markedly better because it's going to depend on your data, but you're not going to risk a branch prediction miss, right? This is straight linear code. This is kind of the main point of the whole presentation, actually. We got to it pretty quick. But that's essentially, Clang is showing, a little nicer performance here, at least on ARM. If we go to X86, same thing, C move no. It's the same type of thing. It's returning one value or the other based on a flag result. And again, no branching. I found it interesting, Clang does this and GCC does not. At the time I did this, the MSVC compiler did not support this feature set yet, so I didn't try it. Okay, subtraction and multiplication follow the same general pattern. Right, so some are a little more complex, but just by an instruction or two, but it's the same general type of thing. Division, I thought was kind of interesting. In this case, it's doing a comparison, and then it does a branch, depending on if it decides if it needs to, and then it returns, or it does the operation and returns the value. So the division's a little bit different pattern. I thought was kind of interesting. X64 does essentially the same thing. It's comparing and then jumping as needed. And in this case, Clang does the same thing. It's also got a branch. Yeah.
So what happens if one of the arguments you're dividing by just happens to be 0? Does it find a way to clamp that at positive or negative max, or does it still return not a number?
I think it's going to end up not a number in that case. Yeah, at least in this example, there's nothing, I don't see a test for 0 on either of them. Back up to that one. Yeah, it's the same constants it's testing for. So it's testing the boundaries and then just goes through. So I'd say if you're dividing by 0, it's going to either return not a number, or it's going to throw an exception and abort the program, depending on how you've got the environment set up. Yeah.
Does this only operate on integer types?
I only captured them for integer types. Well, it does only operate on integer types, yes. And that's in the spec.
So no floats.
No floats. Yeah, if you go back up to the spec, yeah, and this is basically straight off of CPP reference, but yeah, it specifies 2 integers. Okay. Yeah, again, Clang does essentially the same thing. And let's see. I have the constant of the. Yeah, and for X86, again, it's pretty similar. Oh, okay, that one's got the jump done a little differently, but it's essentially the same thing. You have the key is you have a branch. Okay, alternatives for ARM. If you're working on ARM, there's the neon instruction set. There's a Q modifier that lets you set this directly in the assembly language instruction. So basically, I just put in the, if you really want to get into that, I've got the whole spec there in the link. But basically, it's VQ add, and then S16, and then the register set. And then the processor just does it directly. And for X86, it's packed unsigned saturated add. And it's the same type of thing. It's just a specific opcode that moves it down to the processor level. If you really need the performance, use the assembly. You can probably, I should have looked at this and I didn't think of it until just now. Looked at the, put in what the intrinsics were for these assembly instructions if you're using intrinsics. Okay, like I said, this is a pretty short one. The Compiler Explorer Playground I was using is listed up there, should still be around. The P0543R3 spec is listed, CPP reference, compiler support, and that's what we got. So questions, comments, concerns? Kind of a short one tonight.
I think I already asked all my questions.
Okay.
Yeah, I have a question. This is Bob. You talked about returning not a number if the denominator is 0, the divide operation, but not a number is a thing for floating point numbers. It's not a thing for any integer type.
Good point.
What's done then?
That it's going to throw an exception.
Yeah.
You're going to get a divide by 0 exception. Yeah, good point. I didn't catch that when we were doing it. We're talking about that one.
Thank you.
Yep. The other one we can talk through a little bit or poke at is CUDA stuff. I didn't include it in the deck because it was kind of out of spec, and I didn't actually think this was going to go quite as quick as it did. I was expecting about 45 minutes, not a half an hour. But CUDA has modes that you can set on the GPU that turn on and off saturation arithmetic. And the discussion we were having, prior to the meeting where this came up, we got into the CUDA stuff a little bit, and it's essentially a flag, a mode that you set on the processor. And I believe you really need it, look it up, but I believe it's all or none when you're working in CUDA. So you set the entire processor to saturate or not saturate. And that's kind of what the granularity you get, which may not be what you need. If you get into CUDA, you can, the more advanced programs, you can run multiple. Well, CUDA breaks things out into warps and then the stream processors and down this hardware hierarchy. You can run multiple processes on different subsets of the GPU at one time. I believe the flag still affects everything. I don't believe it's per stream processor, but double check me on that. I could have that wrong.
Hearing that very much makes me want to just do it all by hand in CUDA and not trust.
Yeah. Yep. And think. Yeah, you have to double check that. I haven't gotten that deep into the CUDA stuff to know for sure. And I'm going to throw the other caveat in there. I bet it depends or would depend on which specific processor you've got, which hardware revision, or not hardware revision, but CUDA capabilities. If they're going to change it, the old ones I'm sure didn't have it because you couldn't even do different program counters on the older hardware, much less anything else. Yeah, Robert.
Yeah. Yes. It's more of an observation, but I think this is the first time in all the lectures here and other places where we've looked at the assembly language produced by the compiler on different platforms to see how they implemented the feature. Usually we just talk about the feature and how it works.
Yeah. We've done it. I know we've done it a couple of times. It's not common. I went down that path for this one because you don't need the saturation arithmetic library feature to do this, right? I mean, C and C++ have been around for decades, and you've been able to do this, detect saturation and overflow and underflow and things by if then state or if else statements at the code level.
Right.
But it's not efficient, right? So at least in my mind, the real benefit of this library is not, it's giving you something you couldn't do before because you could. It's giving you a more efficient way to do it because it's pushing this down to the assembly. So it made sense to, hey, let's go look at the assembly.
Yeah, that's great. And it makes it easier to understand the code too. Somebody doesn't have to look through all this if then else logic to figure out what he's trying to do.
Yeah.
Yeah.
The other thing I didn't get into, I've run into this on various other processors. So we're like in the C language, for instance, and on, for instance, DSP type processors, right? It's not standardized. Everybody has their own implementation. But it's, especially on DSPs, it's very common to have some type of system configuration flag or hardware configuration flag that turns this on or off for the DSP processor, right? So that's pretty typically done, and you set some register bit somewhere that tells it to saturate or not saturate. And I didn't get into that because it's totally processor specific, but if you're working low level on a DSP or some architecture designed directly to do some of these things, you can find that deeper down. So that's another alternative that you've got if you've got the hardware support. Again, it's going to be similar to kind of what CUDA does, I think. You're just flipping a bit on the processor and saying, hey, I want the ALU to work this way. Yeah.
One question. How does this look in the header files? Is it implemented as a set of overloads, or is it implemented as a template? And if it's implemented as a template, you have the opportunity to define your own data types and overload it based on the underlying data type that you're using for your data type. And that's a way that you could implement your own limits that are not the same as the hardware limits, that the limits could be characteristic of the data type.
Yep.
Is it templates or is it overloads?
No, it is absolutely a template. Let me scroll back up here for a second. Yep. So it's defined in header numeric, where they come from. And
so if you define it,
and this is from cppreference.com. So it's defined in the header numeric, and all of them are function templates.
So you could define your own overloads.
You could, yes.
To have their own limits that are within the limits of the underlying data type.
Yeah, so that actually gets to your question. You could do it that way. Yeah, good point.
Yeah.
But aren't what you're doing dependent upon detecting a condition code after like your addition instruction?
Yeah.
And if you're choosing a data type that doesn't match one on the architecture of the chip,
Oh, yeah.
then
Yes.
you're not going to get a condition code. So
That's true. You
how
could,
is your library code going to
Yeah,
handle the two cases properly?
I think he's got the neck. So from your side, Robert, you could set the upper and lower limits, but the detection is the overflow bit on the processor. So it would not trigger.
Well, what I'm thinking of is that if you have a data type, if you have a data type that's based on one of the standard data types, then you would implement that, but you want to tighten the limits down. You would implement this by calling the library function on the underlying data type to make sure that it's within the limits of the underlying data type, and then test your own limits and squeeze it in further if you need to.
I see what you're saying. Okay. So basically so basically if you wanted to clamp to 0 to 32, you would do this, and then you would come back and say in the template, if greater than 32, set it to 32. You kind of using what you would do in the past, right?
Right.
Okay. I can see, I'm not sure if that, let me think that through a second. Yeah, that still does give you a benefit, because if you just tried to test against 32, for instance, and you wrapped around,
Yeah.
you would get the wrong answer.
No,
So
you'd have to first use the saturated add on your underlying data type, and then
yeah, it's a two-layer thing. Yeah. So yeah, you would still, and basically if you did it straight in code without using the overflow bit, you'd still have to, I think you'd still have to make two comparisons. One to see if you went out of bounds of the, let me think about that. No,
you'd have to do your arithmetic in the next larger data type.
Yeah,
And that's really complicated.
Yeah.
I like this saturated library with the standard implementations can solve the wraparound problem.
Yep.
And then you can squeeze it further if necessary.
Yeah. If nothing else, it would absolutely make the code easier to understand.
Yeah.
Because I'm trying to go through the mental gyration now, going through all the conditions that would result in an overflow or a wraparound condition, and then figure out how to shrink the range down to, whatever I need, 0 to 32 in this case. And then look at all the possible interactions or possible edge cases that could result from the two interacting. This one basically gives you one test almost for free, especially if you're using Clang. And then you get and then you do the other tests. So it may not be the most performant way. I keep wanting to think there's a way you could do it with one test, but I'm not comfortable off the cuff saying it's going to be right in every case.
Yeah, the only alternative I can think of is to do your underlying arithmetic in a larger data type.
Yeah.
Before you do your
and then clamp it.
But this may be better. I don't know.
Yeah, and that assumes you've got a larger data type. If you're working on, say, a 32-bit processor, right?
Yeah.
And you've got a potential 32-bit result. There is no larger data. Well, there is, but you're going to cause the processor to do two additions and all that complexity. Right. So.
Right.
Yeah, it's definitely, at least in some cases, it's definitely an advantage.
Yep. Thank you. I could use that for sound.
Yes. Yeah, this works. I would say this works probably, better than any alternative I've seen for sound, right? Because if you wrap around, you're going to get a much larger deviation.
Oh, yeah.
Than if you just clamp, right? If you
That
clamp,
sounds ugly. They're pops.
right, that's going to pop versus a frequency distortion, which
Yeah.
may or may not get heard.
Right.
Okay, other thoughts, comments, topics we would like to go? We've got, a whole another 50 minutes. Apologies for this one being short. I thought it was going to be longer than, when I went through it myself, it was longer than I went through it here, so.
Yeah, I would, it would be interesting to me if you did another, I mean, if you do give this talk again, you might make a second half in the floating point world,
Okay,
because there's where a lot of the arithmetic that's done in signal processing is really floating point arithmetic.
yeah.
And this
And
is, and it's in signal processing that this would be most useful.
Yep. Yeah, and actually most of the stuff I've seen in, stuff I've done in signal processing, at least it's tend to been on like microcontrollers and stuff, so it's been integer domain.
Yeah.
I've got a brother-in-law who's done audio processing on DSPs, and he's always in 32-bit float land.
Yep.
So,
Yep.
Just simply because, which actually surprised me. If you haven't done that, it turns out you, I wish it was Jalen. It's one of the guys here that does this. Turns out you need the precision to make it sound good, in the floating point world. Integer kind of works, but it's not as good as floating point. I found the first time I heard that was counterintuitive. Video, you can get away with integer all the time, right? You don't need floating point doing machine vision type work, at least that I've done. But audio wants the floating point more often.
Yeah. Yep. And it's etc. You want to, well, when you get to the hardware, it's going to be integer. But when you're doing your processing to create this the sound, it's going to be floating point. Mostly.
That's interesting, yeah, because everything I've always done has been integer domain with this type of stuff.
Yep.
You see my eyes darting around. I'm not crazy. There's a fly running around here that's driving me nuts. Anybody watching, why is Lloyd doing this? Anyway, keeps flying through the light right above me and reflecting. Annoying. Anyway, that's a total here, not there. Yeah, it'd be interesting. Do you have any insight into why that is? Because I've heard floating point is what you want to use if you can. To me, at least, it seems counterintuitive, but it also seems like there's some mathematical reason or something behind it that gives that more justification. In the case, let me qualify that just a bit further. In the cases where I've done this myself, I was always going from an analog to digital converter through some, conversion or transform back to a digital to analog converter, right? And because, both of the A to D and the ADC and the DAC are integer devices by nature. Integer was always enough for what I was doing. It just strikes me as a little counterintuitive that you'd want to go to floating point in the middle, and take that, take the conversion overhead. I don't know, do you have any insight into what's behind that?
Some. The things you want to do are things like filters and delays, which are sometimes often fairly high order operations where you're taking a big hunk of data and doing a fairly complex piece of arithmetic on it, you never know when the intermediate data values that you're generating within that hunk of data is going to be outside the range of your integer.
Yeah.
You still need the bits, but it also is important to have the dynamic range.
Mm-hmm.
And when you need dynamic range, you use floating point. Also, there's another reason, because you really, for example, in sound, the absolute value of your values at, say, 1 meter range is going to be hugely different from the absolute value of your values at a kilometer range.
Yep.
It's, you've got your 1 over r squared, or your 1 over r, I guess, for the value, and then you've got absorption in between, and whatever goes on in between there. There's a huge dynamic range of the physical quantities being represented. And the physical and the where you want to work, the place that you want to work conceptually in between is in the units of the physical quantities, which can have a huge range. Now, eventually, if you want to go back to hardware, you'll have to know more precisely what the range of your hardware is to go back to hardware. But you don't always want to do that. If you're in a simulation, for example, you figure out what the dynamic range of your answer is, and then maybe you go to integer for representing it. But all of these signals that I produce are produced first in floating point, and if necessary to make them listenable, you put them through a DAC and listen to it. But mostly you don't. Mostly you want to put it on a display that might actually have color coding that's logarithmic. But you don't want to work with those logarithmic quantities. You want to work with the physical quantities. The actual sound pressure, which has a huge dynamic range. So yes, to do all of that arithmetic, and mostly, and it's only until you come to display it or listen to it that you do something different. In all of the intermediate processes, you want to do it in something that has a dynamic range that supports the physical quantities that you're working with, which can have a huge dynamic range.
Okay, that's interesting, because one of the applications that I was working with on this, and I believe it wasn't actually sound, it was radio signals, right? We processed it as sound, but it was receiving ultra low bit rate. They were actually magnetics, but it was radio transmissions, right? So we were demodulating a radio signal fundamentally. What we had was a gain setting. Now, we didn't actually use it. We'd set the gain, so you had a gain control, essentially an amplifier on the input to your A to D converter. You'd set the gain control to whatever gain was appropriate to get you in range of the ADC. Yeah. And then you just left, for our application, you just left it alone. But I could see a much more sophisticated application, which would have had to have better hardware than we had too. But the gain setting, again, those are typically logarithmic, so you've got a large dynamic range. the gain setting could be combined with the ADC output into a composite value.
That's called floating point.
And that's, yeah, and then exactly, then you're going to be in floating point just by the nature of it.
Right.
Yeah, that's it. Okay, that makes a lot more sense when you start looking at the more complicated applications like that. Huh, cool, thank you. I learned something on this.
Yeah. I did too.
Okay, other topics. We still have a half an hour at least, if we want to, or we could go home early, whichever folks want to do.
I could finish my supper.
Is the point of the divided saturation. You divide by 0, it's probably throw an exception. If you divide by 1, you're getting something within the range. And if you divide by something greater than 1, you're also getting a value within.
That's a good question.
So what's the purpose?
Bob, do you know on that one for divided set? Oh, I'm going to take a guess at this one. It may or may not be valid, but if you're using, so one of the things you can do with integers is use fixed point. Instead of floating point, you do fixed point, right? So you basically offset it and say the whole thing's fractional. And at that point, you can be dividing by something between 0 and 1. But I'm trying to think, would that mathematically, when we think about it, it could saturate, right? If you're going to divide by 0.25, right, you're essentially multiplying by 4. But if you're stuck in a complete fixed point domain, I'd have to try that and see if that actually overflows, because I don't think it would. You get a fixed, you're going to get a number out, and it's just going to work because that's the way you've defined your number system. They've included it, so there's got to be something around it. I don't think if there's another.
Yeah.
There's another edge case there that I haven't run into before. So you're dividing two numbers, you're dividing two integers.
Yeah. The other Robert was correct. I think whoever said that you never get a number that's outside the data type you start with.
Yeah.
If you're in the divide.
The numerator is within range, then you could get a divide by 0 error, but other than that,
Yeah.
you're always going to produce
It's going to be within range.
Within the range.
I'm tempted to say that, but I'm also tempted to say we're missing something because they went to defining a whole function for this.
Well,
so
this issue comes up only if you're limiting yourself to integers.
Yeah, which they do. It is integer, but if you look at.
Well, I mean, these particular ones are integer.
Yeah. But they're handling it as if, and it's not just one compiler, it's both compilers are handling it as if there's a boundary case that needs to be handled.
Okay, here's a possibility. How is the template written? Does it have one template type, or two template types, or three template types for the A, B, and the result? And if it's all one template type, then no, you can never get overflow. But if it's different type for the output than for the inputs, then yeah.
Have you divided 64-bit figure by a 32-bit figure, maybe? You could overflow 32.
Yeah.
Generally, the return type doesn't affect the signature of your function.
See if we can look one up real quick. Standard library header.
Right. What does the header look like? How many template parameters?
One template parameter.
Just one.
Right.
So if you're restricted to integer types, then it won't.
Oh, wait.
Oh, there's signed versus unsigned also.
Yeah. Okay, I thought I spoke too soon, but it Saturate Cast has 2 template types, which it would.
If you would, okay.
But
But not but not the
DivSat is
arithmetic.
one. Yeah, DivSat is one template type. I don't know on that one.
You said this is a library feature, not the language feature?
It's a library feature, yeah.
If we could look at the library source code somehow.
Yep, I'm trying to think. Well, it's in numeric. It's just a header function. So I'm trying to see if I could quickly get to. I'm just trying to see. I don't have one. I know exactly where to go grab it. I'm just trying to see if there's a spot where I can grab it quickly off the header off the web. The 23. Yeah. I don't have a good spot off the top of my head where I could just go jump right in and grab a header file.
It can always just be, well, this is for completeness. You got to have all 4 operations.
Yeah, that could be. I was gonna try jumping in. Let's see what am I logged in on this one? Yeah, let's just ask Gemini and see what it says.
Training includes C++26.
I don't know. Let's see what we've got. What do we call it?
Div_sat.
In the C++26. Let's just see what it says to that.
Zoom in a little bit.
Yep.
Yeah, it's good.
All right.
Ah, there's that edge case. Okay, because
Okay, so it's a -1 in the okay.
okay.
So it has to do with signed values.
Yeah.
Oh, in min divided by minus. Yeah, that would do it.
Hey, AI is good for something.
Yeah. An edge case.
Yep, it's an edge case. Okay. And now we've all learned something.
Yep.
Mostly that Gemini knows more than I do.
I'd rather say Gemini knows some things that we don't,
Okay.
because it doesn't know everything we do.
Yeah.
Yeah.
That's true of any pair of people. The Venn diagram of what this one does and then what that one does may have some overlap, but there's always something else.
Yeah. So, something I used to do, I haven't done it much anymore, but when the LLMs first came out, I found it really valuable to take 2 or 3 of them and give them all the same question. Because you would, you would get different answers, just like asking different people. And I suspect it's because they're now training on almost identical, they're all training on all the data type of thing, right? It's not what say is identical, but they're all training on, all the data they can get their hands on, which is hugely overlapping. Doesn't seem to be as much of a benefit as it used to be.
The LLMs are probabilistic, so given the same query, they not necessarily give you the same answer.
Right. Although I do see they tend to give you generally the same, the wording will be different. But the core of the answer I find is the same. And I hope it would be, right?
It'd be interesting to have a web page that submitted everything to each LLM like 4 times. And then put all 12, all the like LLM across each.
And each one down. That would be interesting. Okay. Well, that was a good question.
Yep.
What's the next good question? We've got half an hour left.
And I have other things to do tonight, so I think this has been a very interesting talk. Thank you.
Yeah, thanks. Okay. Well, I guess at that point we can wrap it up and head home a little early.
Thanks, Lloyd. Cool talk.
Or for folks who already are home. Okay. Oh, just quick plug. I am looking for speakers for the second half of the year. So if anybody's interested, let me know. I'm got a reasonable cadre, so I'm not hurting yet. But if somebody wants to do a talk, let me know.
Still working on mine. I'm hoping it'll be done sometime in the second half of this year.
Oh, cool. Because I was going to ask you specifically that question. Okay, well, I will stop sharing. I'll get this stuff posted tomorrow. And I'm going to just, whoops. Here. I'll also remember to stop the recording. Okay, thanks everyone. See you next month.
Looks like just us now.